Hi. Whoa, okay. I told you I have a loud voice. I actually hated my first chemistry teacher, but then they changed her and everything changed. So there is every time someone tells me I hate chemistry, I blame the teacher in their high school. So, yes, my name is Elena Meirzadeh. I recently joined the Weizmann Institute and opened my lab. And what we do in my lab is making new forms of carbon. And I'm going to give you a taste of one of them today. But the reason chemists are loved, obsessed, choose the definition you want with carbon, is that it's the most fascinating element in the periodic table. It can form many different types of chemical bonds, different numbers in different geometries. And if you change slightly every one of those parameters, you get a whole different material. And you are all familiar with these differences in your daily life. Just look at graphite versus diamond. Very expensive, very cheap. But there is a reason for that, and it's the chemical bonding. These differences originate from the way the carbon atoms bond to each other at the atomic level. For diamond, there is a three-dimensional network. The spheres represent the carbon atoms and the lines chemical bonds. And these carbon atoms connect to each other through the strongest chemical bond in nature that are called covalent bonds. On the other hand, for graphite, the structure is a bit different. There are strong covalent bonds in each atomic layer, but very weak chemical interactions between the sheets. And those weak interactions are called van der Waals bonds. Therefore, diamond is the hardest mineral known to humans versus graphite is very soft. It's so soft that you can peel it by pressing it slightly. That's why we use it for pencil. Diamond is transparent. Graphite is opaque, and this one, diamond, is electrically and thermally conducting, while the other one doesn't do either. Other way around. This one is insulator, this one is a conductor. And these two natural allotropes, forms of carbon, fascinated chemists for many, many years, but also challenged them. They looked for new forms of carbons that can be synthetically made. And the first attempt, successful attempt, was in 1985. They took graphite and blasted it with laser. They wanted to introduce a lot of energy and see what happens, what forms. And what they got, they measured the mass of what was formed, and they keep getting a mass that is corresponding to 60 carbon atoms bound to each other. It's very specific. They changed the conditions of the reaction. It kept showing up. And they called it C60. But they didn't have enough material to determine the atomic structure. So they looked for a mathematical solution, and the only way you can explain some entity that has 60 points that are connected to each other to form a stable thing is a soccer ball. They didn't have a crystal structure, so they put an actual picture of a soccer ball in the Nature paper in 1985. And later on, when they improved the synthesis, they solved the structure, and it was actually true, which is incredible. And they called them buckyballs because they reminded them the geodesic domes that Buckminster Fuller used to make. He was an American architect, and they were round, spheric, very stable, and made of hexagonal and pentagonal rings. Now, buckyballs were just the beginning. After them came the carbon nanotubes that look like straws. They're very light, but very strong. So people used them to make fancy mountain bikes. They're very expensive, but robust and light. Then the third cousin came into the picture, graphene, which was fascinating because it's basically like graphite, but they found a way to isolate one atomic layer, and everything changed. A whole new physics emerged because you confine electrons to 2 dimensions instead of bulk, 3 dimensions. And we are chemists, we get bored very easily. We look for more and more complex structures to see how we can further tune the properties. There are many things that you can do. What I did in my postdoc, instead of taking graphite, I took fullerenes, and I made something that is similar to graphene by being 2-dimensional, and that's why we called it graphullerene. So instead of simple elemental carbon being the repeating unit, we have these fat balls, the C60 molecules, that are covalently, very strongly bound to each other in 2 dimensions, but there are weak interactions between the sheets, so we can peel them off. So we call it 2 dimension, but it has another dimension because it's more like a bubble wrap. But this is actually very interesting because the chemistry and the physics will be very different than graphene, that it's right here and simple. Because there are very strong bonds between the fullerenes, we can use a Scotch tape, magic tape. There's nothing magical about it. This is just a brand name. You stick your crystal to the tape, and then you do a bunch of this with another piece of tape. You peel off more and more layers. You put this tape on a substrate, remove it, and you're left with a monolayer of whatever 2-dimensional material you have. This is very helpful because you can make 2D devices and see how the properties, the physical properties, change at the nanoscale versus the bulk. But it also allows you to use electron microscopes to do imaging. For this type of electron microscope, you need a very, very thin sample. This is why we needed to exfoliate it. And you see individual C60 molecules as round spheres, and you can see how they hexagonally pack next to each other, which is incredible. To be able to get such high-resolution image at these scales, you need really good crystals. Now, crystals are periodic. They are basically solid materials that the building blocks repeat in a periodic way, like this one. There are different ways to make it. Our way is a bit more exotic than the normal chemistry that people know. We take the molecules and we cook them to very high temperatures. So you take powders, you grind them, place them into the pellet because we don't have solvents. Normally in chemistry, you put your stuff in a solution, stir, heat up, and let it react. It's like cooking versus baking, I guess. So we press it into a pellet, and then we need to heat it without burning. So we put it inside a quartz tube, seal it under vacuum using a hydrogen torch. It glows because we need to melt the quartz to be able to seal it, and the melting point is very high. The torch gets to 2800 degrees C. So you need to be also very careful. Once you have it's like a tiny reactor that you make. You take this reactor, you place it inside an oven. For making graphullerene, I took C60 and used magnesium. The reason I took magnesium is that it loves to give electrons. It's a good reducing agent. It gives electrons to C60, and then these C60s, it's like they have more arms to bind to each other using these extra electrons. Then we put it inside the temperature gradient because you need, this gradient allows them to react slowly and carefully, and then you grow your crystals at the colder end of the tube. And you grow these beautiful single crystals. This is a simple optical microscope, not an electron microscope. And this is the crystal structure that we determined using X-ray diffraction. So the X-ray beam reacts, basically hits the atoms, gets scattered, and by the way it gets diffracted, we can go back and tell what is exactly the position of each atom and chemical bond. The green spots are magnesium. I told you I'm making forms of carbon, so we got rid of them, put the crystals in acid. The acid binds the magnesium, pulls it out of the crystal, and you end up with a pure carbon-based material. Graphullerene itself opened a whole new direction in chemistry, like fullerenes, nanotubes, and graphene. By itself, it has a whole different type of properties. All the electronic conductivity, thermal conductivity, the optical properties are different, and we're going to investigate that. But besides that, we're going to make more of this family. We call them the superatomic family. The reason is that it's not just us, we're not weirdos. It's because these fullerenes, they're like atoms, but much bigger. So they call them superatoms. And there are many types of them. So we started with changing the reaction conditions, still magnesium, but slightly change the reaction, like temperature and stuff. You can change the structure. You can go from hexagonally to rectangular sheets. These differences in chemical bonds and geometry changed all the properties of these materials. Magnesium is one type of alkali earth metal. There are more alkali metals and alkali earth metals. Each one of them has slightly different properties. Some of them like more to give electrons, some like less. They have different melting point, different vapor pressure. All of these things change what we get at the end. We want to make magnetic superatomic crystals because they have future potential applications for quantum computing. So we can take magnetic transition metals like chromium, iron, cobalt, and nickel. And we're going to take different fullerenes as building blocks for starting materials, like C70 or brominated C60 that has tons of bromines on top of it, or lithium C60 that has a lithium ion trapped inside the fullerene. It's like a cage. And we're going to study how these trapped ions interact with each other, interact with the cage, and maybe use them as quantum bits. Maybe, one day, hopefully. They're the most expensive, one of the most expensive materials in the world. Thank you, Azrieli Foundation. So with that, I want to thank my amazing team. I have a few students. We just finished their renovations literally last week. So this is my brand new lab in the oldest building in the Weizmann Institute. Chaim Weizmann lab is above us. It's really nice to work in such a historical monument in the Weizmann Institute. And I want to thank Azrieli Foundation, Weizmann, and you.